Let's take a look at another matrix inversion problem. So matrix inversion number 2. We're actually going to look at the exact same matrix as we looked at in the previous video. The matrix A equals 4 and negative 2, 2, 3. And we're going to answer the exact same question. If it exists, find A inverse. The difference is, in this example, we're going to use an equation specific to 2 by 2 matrices. In the previous video, we used an algorithm that lets you compute the inverse of any square matrix. Remember what the algorithm was? You take your original matrix A and you form an augmented matrix AI, where I is an identity matrix, and then you perform row operations until you end up with a reduced matrix of the form I, A inverse. So you can use that approach to tackle computing the inverse for any square matrix. In this video example, though, we're going to show an equation that lets you easily compute the inverse of a 2 by 2 matrix. So the first thing we're going to do is we're going to check for the existence of the inverse. We know that the inverse exists as long as the determinant is not equal to 0. So computing the determinant of a 2 by 2 matrix is very easy. It's just this element times this element minus this element times this element. So that's what we've done right here. 4 times 3 minus a negative 2 times 2, so that is equal to 12, minus a negative 4, which is 12 plus 4, which is 16. So since the determinant of this matrix is 16, which is not 0, then we know that A inverse does indeed exist. So now that we know that it exists, let's go ahead and compute the inverse. So here's where we're going to show the specific equation for the inverse of a 2 by 2 matrix. So for 2 by 2 matrices, they have a form in general of A, B, C, D. The inverse can always be written as 1 over the determinant of A times this matrix right here. So note what's happened. Originally we had a matrix A, B, C, D. A and D have flipped spots. So along this diagonal we used to have A, D. Now we have D, A. So they've changed where they were located. And then on the other kind of diagonal, so to speak, we had B and C. Well, B and C are still here, but it's now negative B and negative C. So this is a nice closed form equation that lets us just write down exactly what the inverse of a 2 by 2 matrix is. And it's very clear why the determinant not being 0 is so important. We're dividing by the determinant of the matrix, 1 over the determinant. So for the determinant to exist, this quantity can't be 0. So that's why we check this off the bat to make sure it's not equal to 0. So let's go ahead and use this equation now for this specific case of A being the matrix 4, negative 2, 2, 3. So this is equal to 1 over AD minus BC, that's what I computed up here, times the matrix D, negative B, negative C, A. So let's go ahead and just plug in all these values. So A inverse is 1 over 16, because we already did that computation right here. And then the matrix becomes D is equal to 3, so I'm going to put a 3 there. B in my original matrix is negative 2, so I need to write down a negative B, so that turns into a positive 2. What goes right here is negative C. C in my original matrix was 2, so I need to write down a negative 2 there. And then finally what goes right here is A. A in my original equation was 4, so I'm going to put a 4 there. So this is A inverse. I could just stop there. This is a totally legitimate expression for A inverse. I'm going to go ahead and distribute the 16 though, or the 1 over 16, so that's 3/16. 2 over 16 is an eighth, and negative 2 over 16 is a negative eighth, 4 over 16 is a fourth. So you'll note this is the exact same answer as we had in the previous video, which it has to be because we're computing the exact same quantity. The only difference here is we use this general expression for, or I'm sorry, a non-general expression. This expression is specific to 2 by 2 matrices.